Hello, and welcome to Class 9 of Particle Fundamentals and Fuzzy Logic. So in this class, we're going to expand on the previous class as far as variation, and we're going to apply it to quite a few different circumstances and come up with a few more testing scenarios to carry those out. The other thing we're going to do is we're going to take a look at how to dynamically set these things not only at the SOPs level, but during the sim. So let's see how we can carry that out. All right, so I'm going to make a new testing scenario because, as I've said before, we always want to go based on most important to least important because it's almost impossible to judge all these factors at once. Here, we've even just got a few factors in play, just one even, the variation here, but we also really can't tell if it's actually the variation or if it's just the noise in the current, or, it becomes harder and harder to tell. So for that, let's take out, once again, the global ocean current. And let's take out the current in the up vector. And now we're purely left with the speed variation, and we don't have any side-to-side movement. Okay, and now I want to test some rotation, because I think probably the second most important factor of this whole thing is the left and right turn direction and adaptation. So let's come up with a rotational test scenario. For that, maybe I want them all aligned more or less in the same spot. So this line I'm using here, let's turn that into a different line. So I'm going to make a line at the origin, maybe with a length of 3, and let's get about 10 sharks in play. And then I'm going to switch a target from left to right using our same switch method as before. So here's the start of the target. And I'm going to switch between the sharks, trying to rotate to this direction, and the sharks rotating to that direction. Okay, so let's plug that into our switch. Okay, and then the initial line, that'll just go into here. And let's see what happens. Okay, so it's definitely rotating, but I want to take out, in this instance, just so we can judge the rotation, I want to take out the seeking behavior. There we go. And after about 10 seconds, it should switch over there. And just for better testing, let's decrease that interval a little bit, so maybe every 6 seconds. That'll be pretty good to test with. Now, diving in, let's find a few relevant settings that we can adjust. So the obvious place to start is the shark left-right direction. And here we have a detect degrees and the strength of the rotation. So let's just test that out a little bit. So if we make the strength really, really high, we should expect a much faster turn. Yep, get a really fast turn. Pretty low. Also visualizing the vectors in play. Notice that it still moves pretty fast, even if I put in the rotation degree. And that's because it's conflicting with the tilting axis. So I'm just going to turn this off right now. It's just right now it's just going to like run into errors. Not even so much errors, just like difficulties, because it's going to be overcompensating in a lesser important axis. So let's just temporarily turn off the shark tilt here. And now we can really see the slowness or the fastness of the turn. Okay, so let's get a good low value, maybe a big shark. Let's figure out what that might be. So at this, I'm going to test on the SOPS level, because I think this would be more of a consistent behavior throughout the time. So we'll put that back to a pretty good default. So let's see, where is that at? Around 130. And let's get the name of that parameter, which is rotate deg. Okay, so we really have to watch out here, because there could potentially be something else in our system that also has rotate deg. And I think I want this to be more of an overt name. See, here we have turn deg. It's not a very good name. So as we're going through our system, we want to clean things up now that the major dev is finished. Okay, so here's our rotate deg. We want our default value to be around 130, and we can call this shark dir, shark dir rotate deg. Okay, and I'm going to copy that. Let's make sure it still works. Okay, and that's a pretty good default value. And now let's go up into our add-ons here, our variational add-ons. From the previous class, this would be pulse intensity high. And I'm going to make a new one. So we have to decide, is this going to be driven by the size? And I do think it will be driven by the size, but to a lesser amount. But I'm still going to enable the grad p scale to feed into this. Okay, so this will be our shark direction rotate deg. And we don't even really have to adjust things at the particle level, because we've got everything we need right here. So let's find a good low value for a really kind of slow, lazy, big shark. So let's just start off with 50 degrees per second. Really slow. I don't think a shark would ever really react that slowly. Let's try 100. Yeah, I think that's about right. Okay, maybe 93. Okay, so say that's pretty slow. And they're both the same, but okay, so if the shark is small, okay, then do we want it to rotate faster or slower? In this case, I do think it should be more frenetic once again, so I'm going to have that rotate faster. And this will be slower. Now, I think it's a bit too exponential driving from the p-scale. So instead, I'm going to drive from the rand p-scale instead of the grad p-scale. Okay, and now let's get the high value. We haven't really done any variation. We've just made it set to be ready, and now let's get the high value. So if this is the slow shark, let's figure out the fast one. I think even faster. Okay. And now let's see how the variation plays out. Right now it's completely driven by the p-scale. Okay. Cool. And maybe even more extreme for that. Okay, so now let's mix in some random. So I want to have a different seed than potentially something upstream. And how much randomness do we think this is going to be? Well, I'm actually going to go a little more variation per shark than previously. All right. And now if we can see the combined effect with two sharks put together. So let's switch this back to our sharks in a row. There we are. We won't see much action here because they're not swimming yet. So let's enable the swim, as well as the tilt. And we just have to take a quick look at this tilt just to make sure it's not reacting too violently. And okay, so that's probably okay. I'm just going to decrease this amount just a little bit. Let's see what happens. All right, so now we've got two factors in play. And we see even more variation than before. Okay, so we can see how this can quickly become something where we really can't tell what's going on. And it's really important to test at each stage so we can get the right amount of variation. Okay, so now one thing I'm noticing after we've had the rotation and the speed difference is I'm noticing that they all really do tend to take off at the same time, and they tend to swim in the same relative direction to each other, as well as they have their speed differences. But I think it'd be good if they actually saw the target a little differently, and we can do that in a few ways. So one way I want to try to integrate that is by making their attention to the target a little different. So we can do that by varying the actual target distance. In the seeking behavior, we have some speed variation programmed into the intensity, but I actually think I want to adjust the seeking distance itself. So let's reinvigorate our test A scenario, our test A attribute, and they all have exactly the same seeking distance. Okay, and let's give that some variation. Okay, so let's get the name of that. That would be shark seek distance high. All right. Okay. And let's say we want to start off and try to find the lowest possible seeking distance. So here, it's just completely let's get a full random going as well. Okay, so here, it's just completely always interested. If we have a really low value, they're always just swimming around. They're always going to be approaching their target. And okay, so we definitely need them to lose interest after a certain point. So what is the most interested they're ever going to be in their target? Let's try a value of 3. And actually, I'm going to do a linear curve just for testing, just for a, okay. Okay, so it definitely gets lower, the interest level, as it goes away here. But they're always pretty interested. Let's see. Okay, so that's how much they're swimming around. Let's have a minimum of 2.5, and actually, so that's going to be kind of the most interested they're going to be. It's easier for me to think about it that way. Now, the least interested they're going to be, let's try something a little higher than 5. Let's try 8. So they're still pretty darn interested after that. So 9. Okay, and if we wanted to test things out a little farther, we could take out anything that's going to affect our distances. Okay. And now we can see that they have some variation as they approach their target. So that could be a really good complement. All right, so should this be completely random? Well, no, I think I want the smaller sharks to be more frenetic and always swimming than the bigger sharks. So the maximum output, once again, is going to go to the smaller sharks, lowest to the bigger ones. But I want to mix in not too much of that. I think they're going to have generally unrelated interest values. And a new seed for the unrelated interest values. And now we're getting some really nice variation in there. So you're just going to eventually start to get some random, seemingly random decisions made by only 1 or 2 sharks. And that's really where I think that magic and that perceived quality is starting to happen. It's almost like they're doing things as a whole, but we don't really know what it is. Okay, so we've got 3 really crucial variation elements. Now let's try to integrate something a bit more dynamic that's in a constant state of change throughout the simulation. What I'd like to do now is actually add some noise to the target itself. So we can do that at the SOPs level, but how do we do that dynamically during the simulation? How do we affect the target? Well, first let's change our testing scenario a little bit again. So with this line, let's go ahead and put them all in the same position. Okay. And now the only thing we're seeing is the speed and rotational variation here. Okay. I'm going to turn off the fuzzy qualities. And now we have identical sharks. Okay, and that gets really easy to test. Okay, so I want to see this target moving around. How do we do that? So in the system, dynamically, we wouldn't put a noise on the shark itself, on the particle itself, on the position there. We would apply the noise to the target location. So here's where we're getting the target vector. I'm going to kind of bring this over to the side a little bit. And because these operations might require a lot of testing, they're more environmental. I'm going to keep these more or less in separate nodes so that they're very easy to turn on and off. Okay, and let's say add noise target behavior. That'll be our system we're going to design now. Okay, so this target vector, we could think about this vector like a vector, like a line, but we could also think about it like a position in space. Okay, and with the position in space, we can apply some noise to it. So in comes our target vector, target vec. And the problem is that if we read this in and apply something to it, then it's actually going to be changed for the next frame and then changed for the next frame. So in this case, I actually don't want a feedback loop because there's no telling our targets might eventually be completely unrelated to whatever input we give our system. So this will be exporting the target vector, and I want to kind of abstractify this gather target vector system. Okay, so instead of exporting the target vec, I'm going to say target vec absolute. Okay, and just because I want to be able to turn on and off the system, we'll also set the target vec in the same step, but we'll override it. So by default, we're exporting target vec absolute. Okay, now we're going to overwrite the target vec on this very next step. So I want to import target vec absolute that will never change. Okay, and let's just make a little diagnostic for that. And let's make this black. Okay, so here's our target vec absolute. And now the actual target, I want to apply some swishy swashy noise just so that the sharks are kind of seeking a moving target. Export when input is connected. And let's apply some anti-alias flow noise to this vector. So I want to treat this as a position. And I want its actual position in 3D space. So for that, we're going to have to take this and add the current position to it. Let's test this location out. Make sure to disconnect any other testing mechanisms you have downstream. So it doesn't, it's not very useful to view it like this, even though we have successfully added the current position to the vector. So it's much more useful in this case to view a location in space as a point trail. And that feature is quite useful. Okay, so now we can see exactly where the target is, and we know it's represented by this position right here. Okay, so now I'm going to be able to apply a consistent noise to this position. And here's the noise, it's driven by this, and now we're going to add this noise pattern to this position in space. And we should expect a little bit of an offset there. Now by animating this noise, we can move the offset around. So I'm going to promote all these parameters. Okay, so I'm going to take the roughness down to 0. Let's link the frequencies together because I can't see a difference of why it would be different in an axis. And let's see how far we want this thing to move. Here's the offset. Okay, so wiggling this around, that's quite a bit of variation for the target, but maybe not that much if it's way back here. We'd expect that target to kind of change pretty far from back here. Okay, so last thing I'm going to do is I'm going to animate this by plugging in the time. And we can call this noise rate by making a new parameter here. Shark target noise rate maximum. So I'm going to add this to a logical axis, which is almost always the y-axis. And let's get a vector. Okay, and actually it wouldn't be adding, it'd be multiplying a value of 1 by this amount. Okay, so here's our vector, multiplying. Now we have up that's progressing along time, and then I'm going to add that to the offset of the noise. Okay, so now let's see if our target moves around. Okay, it's not because our rate is 0. 1 meter per second. And that's really moving around. Okay, it's not affecting the shark yet, but it's definitely moving around our test vector. Okay, so it's a little fast. So let's try either less amplitude or maybe a decreased rate. Actually, just for lack of confusion, let's take out the velocity for now. And we're just paying attention to this. Okay, so we can expect that as the shark is this far away, our target is moving. Our target location is moving like that. Okay. Maybe a bit of roughness for some fractal variation. Okay. Now, right now we could have done this at SOP's level. What we probably couldn't have done at SOP's level is make this adapt to how close or far away the shark is. So now I'm going to get another noise, and let's make that adapt based on distance. Okay, so here's another noise. Let's call this, instead of frequency on both, we're going to adjust these independently. So let's give this a prefix. I've gone ahead and prefixed these values: far frequency, near frequency, etc. Okay, now let's test out the near frequency. So I'm going to add that. So we can imagine the shark is pretty close, and we want a much smaller but more frenetic motion, because as it approaches its target, it's going to become much more erratic and swim more violently. So let's see. So we probably actually want a higher frequency. And we actually want another rate as well. So let's encapsulate this. Okay, so here's a target noise rate far, and let's make a target noise rate near. Okay. Okay, so you have two completely different noise patterns. So let's get a representative noise if it's near. So we want it to be higher frequency and also more frenetic. Let's be even more frenetic. Yeah, something like that. Maybe a touch more amplitude. Amplitude is how strong away from the target these positions are going to be. Okay, so we might see where this is going already, but now we're going to blend between these two things based on how close or far away the shark is. And that's really why we need the interactive component to the simulation. We can't really detect that before the sim starts. We have to do that during the simulation. So any change you want to happen during the simulation, that's where we have to use the particle attributes instead. Okay, so we're gonna mix these two noise patterns together. And what do we want to mix them by? So we definitely want to mix them by how close or far away the shark thinks it is. And now that is different per shark. So as we're gathering the in the seeking behavior, as we're gathering this relative distance, so here's the seek distance ramp. That's the relative amount that it thinks it is close and far away from the target. So let's export that as an attribute. We'll call this shark distance relative. And this can inform a lot of other things. And this is really, once you get a full system going, this is really a fascinating part, I think, is making all these internal connections. Okay, so this is our shark distance relative to the target. It goes from 0 to 1. And now that'll actually affect its behavior as well. So bringing that in, here's our shark distance relative. So now let's see if that works. So it should be low frequency right now. And actually the ramp would be informing more of an inverse. It's far away, so it's gonna swim fast. So we need to do a complement to that ramp. There we go. Okay, so it's far away, and then as it swims closer, it's going to become more frenetic. So let's activate the swimming again. That would be in the seeking behavior. Let's activate the velocity. So the target's right around there. And notice it gets higher and higher frequency as the shark approaches. Okay. And now finally, let's actually apply it to the adjusted target. So let's view the target vector. Here's the yellow one now, it's the target vector. Okay, so let's apply this position to the target vector. So just like we added, I'm going to subtract the position and this updated position to form the new target vector. And it's backwards. There we go. See how that plays out. Okay. And now it's might not be too noticeable because these aren't really that big of differences. It might alter the trajectory just a little bit, but once we put all these sharks together, it'll become a quite dramatic effect. So we also might want different targets for different sharks. We want to offset this noise pattern. So at this point, I'm going to get the shark ID. Okay, so this is going to be different per particle. Here's the ID. integer to float, multiply add constant. Let's vary that. This would have zero similarity to any size or anything like that, any other attribute. Okay, so in comes a good seed. We'll generate a random value off of that, and we're just going to offset this noise. Okay, so let's multiply this by a pretty big amount. So maybe an offset of 10. And let's just add this to what's driving the offset. So we could add this to the incoming time. So it's like shark number 1 is offset by 3 seconds. Shark number 2 is offset by 5 seconds. We'll call this apply offset by ID. Let's connect both of them. All right, so now we can see multiple targets per shark and all the interesting variation that that might have. Low frequency going to high frequency. Finally, let's add in our fuzzy variation. And let's add in the ocean current. And we should have a really nice and varied look. See, we get that odd shark or two that just are responding differently based on just summations of forces. Okay. And it's been a while since we've watched the deforming shark, so let's see how that variation affected how these things look together. And we can see a lot more variation. If we didn't know where the targets were, we would really think that these sharks were having different thoughts and reactions to their prey or their target. Okay. And now let's try it in mass with lots and lots of sharks. And here we can see lots of nice variation. They should all have a slightly different character. And that's what happens when we kind of sum all of those different factors together and sum all of those different forces in play in time. So that's just a few ways to add some natural variation. In the next lesson, we're going to take a look at some advanced tracking and make the sharks circle their prey.